So in this video, we're going to be looking at Manganate 7 redox titrations, right? Now, redox titrations are very similar to what you've done before in terms of acid-base titrations, but there's two main differences. The first difference is, of course, we're looking at a redox reaction, not an acid-base reaction itself. Now, the second difference is going to be, of course, we're dealing with color changes. In terms of an acid-base titration, we use an indicator, and that could be something like methyl orange or phenolphthalein. But in the case, of course, redox titrations, because we're dealing with transition metal compounds, they normally have a specific color to them. Now, starting off, we know that, of course, manganate titrations is going to involve manganate ions, which we know as MnO4-. Now, MnO4- it's not actually going to exist like that on its own. We've actually got rid of the spectator ion, and we could really have something like potassium manganate itself. Now, of course, that's going to go in our burette, and that's going to be our oxidizing agent. Now, this color is going to be very purple. It's going to be like a concentrated Vimto color. Now, the reason why we actually use this is because it's a good oxidizing agent, and when we look at this, right, this actually gets reduced to Mn2+ while oxidizing something else. So yeah, we know that manganate is going to be our oxidizing agent. What does it actually oxidize? Well, it oxidizes normally iron 2+ ions, and it does that to form iron 3+ ions itself as well. Now think back, there's some transformations that you need to remember where you're going from manganate itself to form manganese 2+, and another one where you're going from iron 2+ to form iron 3+ itself. Of course, you can write half equations for both of these oxidation and reduction steps, combine them together, and you end up with an overall equation. And that overall equation actually gives you a ratio of 1:5, which you can actually do calculations with. But yeah, of course, our iron 2+ is going to be pipetted into our conical flask. So now conical flask over here, we're going to have iron 2+, could be something like an iron salt, where we've got the oxidation state of iron being +2. Now it depends on what type of conditions you need. Normally it's going to be acidic conditions, and so you do that by adding in H2SO4 in excess. Now, of course, you can't actually use any other type of acid such as HCl, because manganate, we want it only to oxidize the iron 2+, but instead, if we use HCl, we might end up oxidizing the chloride ions to form chlorine itself. Now, in terms of the half equation, here's what you could end up with: 2 lots of chlorides being oxidized to form chlorine and 2 electrons itself, and we don't want this to happen. So let's say if I were to run my actual practical and I were to release the tap itself, that solution of manganate, which is purple, is going to fall into our conical flask, our solution there, and immediately it's going to decolorize. So what's going to happen in terms of a reaction then? Well, in terms of redox, we end up with manganate that's going to be reduced to form manganese 2+ itself. Now just be aware, manganese 2+, it has a pale pink color. Think manganese, think Japanese cherry blossom trees are going to be pink, aren't they? Now, of course, because we're dealing with dilute solutions, this manganese 2+, it might not actually be visible. It might actually appear to be colorless. Now, what about my endpoint in terms of this titration? Well, if I were to look at it right, I've got manganate, which is going to be purple, iron 2+, which is normally green, but you can't actually see it because it's in a very low concentration. But what's going to happen is going from iron 2+ to 3+, of course, we won't be able to detect any change because the concentrations are so low. But if I've oxidized all of my iron 2+ and I've formed iron 3+, any further manganate that I actually add into the conical flask is actually going to be in excess itself. And so that's what gives rise to this pale pink color, along with the fact, of course, we've got manganese 2+ in there as well. Yeah, so that's how we know our endpoint. It goes from colorless to pink itself. So we've got colorless to pink itself. Yeah, so yeah, moving on, if we were to look at the types of calculations that we can get, basically it's just a normal back titration calculation where you can use it to actually find the concentration of, let's say, iron 2+ in an actual solution. You can use it to find the number of water crystallizations of an iron salt. You can also use it to find the percentage by mass of iron in like a tablet or something like muscular, or you could actually use it to determine the oxidation number changes during a titration itself. Now, of course, if you were to look at it right, the ratio that you need to be able to look at is what's in your burette. It's going to be manganate. It's a 1:5 ratio. What's in your conical flask? It's going to be iron 2+ itself. And you've got to be aware that, of course, to go from here to here, you've got to times by 5. To go in the opposite direction, you've got to divide by 5 itself as well. Now, what we're going to do now is, of course, practice some examples of Manganate 7 titration. Feel free to pause the video and have a go at the following question. Very nice and easy to begin with so far. So yeah, starting off with this question then, we're told 8.45 grams of iron salt was dissolved in 250 centimeters cubed of distilled water. So I've got here a volumetric flask, and in here I'm going to have my standard solution, which is going to be containing 8.45 grams of our iron 2 salt. So not just iron, but iron 2 as a salt. And then we've also got, of course, 250 centimeters cubed of our solution here. Now we're told that 25 centimeters cubed of this solution is going to be taken out, and they're going to put it in a conical flask from where it appears. So we've taken out 25 centimeters cubed, and we're only going to react that amount with 26.6 centimeters cubed of a 0.02 mole per decimeter cube solution of manganate itself. So of course we've done titration, and we ended up with a mean titer value as being 26.60 centimeters cubed, and the concentration, which was known, is going to be 0.02, and that's going to be mole per decimeter cubed itself. I always like to draw these out because it helps me plan out the question, and that's what I've done over here. Now of course we're asked to calculate the molar mass of the iron 2 salt itself. So basically what we need to do is first of all find the moles of our manganate itself. Then we need to find the moles of course our iron 2 plus itself. That's the next step, in 25 centimeters cubed. Scale it up to find the amount in 250 centimeters cubed. Now the final step is, of course, we've got the mass of the actual iron salt itself. We've worked out the moles as well. We can use these together to actually work out a value for the MR of the salt itself. So the first thing that you're going to do is, of course, work out the number of moles of manganate. How are you going to do that? Well, of course, you're going to take the concentration, which is 0.02, times by the actual volume, which is going to be 26.60 divided by 1,000. And so you do that, you put in your calculator, and you end up with 5.32 times 10 to the power of minus 4. That will give you your number of moles to begin with, and that's 1 mark so far. So of course that's our first step done over here. The next thing is I need to find the moles of iron 2 plus in 25 centimeters cubed. How am I going to do that? Well, my ratio here is 1 to 5 itself. So the number of moles of iron 2 plus, and I'm going to be very specific here and say in 25 centimeters cubed, because the examiner might get confused and they won't give you all of the marks if they are confused about what you've worked out the moles for. So the number of moles of iron 2 plus in 25 centimeters cubed is going to be equal to, of course, our value of 5.32 times 10 to the power of minus 4, and that's going to be times by 5 itself. Of course we do that and we end up with 2.66 times 10 to the power of minus 3. That's how many moles we've got of iron 2 plus. There's our next step done over here. Now the thing is, if I've got that many moles in 25 centimeters cubed, how do I find the moles in 250 centimeters cubed? Well, of course, to find the number of moles of iron 2 plus in 250 centimeters cubed, we need to find the number of moles of iron 2 plus in 1 centimeter cube by dividing by 25, and then of course we're going to times by 250 to find the moles in 250 centimeters cubed itself. We do that, and what we end up with is 2.66 times 10 to the power of minus 2, and that's going to be moles itself. I would prefer that you keep these in standard form. Now of course we found the moles there, so we know that 8.45 grams of our salt has of course been dissolved in 250 centimeters cubed. So we know if that's our mass, there's our moles in 250 centimeters cubed. We know that the MR of our iron salt itself is going to be equal to, of course, our mass divided by our moles. So it's going to be, of course, a value of 8.45 divided by 2.66 times 10 to the power of minus 2. And of course, we put that in our calculator, and what we end up with is a value of 318. And that's going to be, of course, grams per moles itself, to, of course, 3 significant figures. And there's our fourth part done there. Yeah. So yeah, this question's out of 4 marks. Let's try another one, which is a bit more difficult, but really it's just combining calculations together. It's quite synoptic. So feel free to pause the video again and have a go at the following question over here. So yeah, in this question, we're told we've got 1.51 grams of steel wire, and that's dissolved in an excess of sulfuric acid, and the solution is made up to 250 centimeters cubed. Now, if they use sulfuric acid, we know, of course, they're just trying to add some protons. They're trying to make the conditions acidic itself, so we end up with iron 2 plus ions 3. So yeah, the first thing that we've got is, of course, 1.51 grams of steel. And we know, of course, that's not going to be iron on its own. That's going to be, of course, our actual iron, and then other metals that are probably in there as well, and other stuff that we don't really know about. But yeah, if we were to continue, we know that, of course, they've dissolved that in a kind of solution to make 250 centimeters cubed. So we've got another standard solution over here. Here's my drawing of a volumetric flask, and of course that volume is 250 centimeters cubed altogether. Now they've told us that they've taken out 25 centimeters cubed of this solution, so they've taken out this iron 2 plus solution again like before, and they've taken out 25 centimeters cubed, and they've reacted it with 25.45 centimeters cubed of a 0.02 mole per decimeter cube solution of manganate ions itself. So yeah, we've got our manganate, which in this case is going to be 25.45 centimeters cubed, and then the concentration is going to be 0.02, and then it's going to be mole per decimeter cubed itself. Now, of course, we're asked to calculate the percentage of iron this time in the steel wire itself. Now, think about it like this: steel is made up of a bunch of different things, and we're asked to find the percentage of iron. So in other words, we're asked to find percentage by mass. So if we look at it right, we've got to find the mass of iron itself, and then we've got to use that to find the percentage by mass, right? So we're going to do this in a bunch of different steps, starting off with the first one, which is going to be, of course, to find the number of moles of manganate, the number of moles then of iron 2 plus in 25 centimeters cubed, of iron 2 plus in 250 centimeters cubed. We need to find the mass of iron, and then hence the percentage by mass of iron as well. So yeah, if we look at it, the first thing that we're going to do is work out the number of moles of manganate ions, and that's going to be equal to, of course, our concentration of 0.02 times by our volume, which is going to be 25.45 divided by 1,000. And we do that, and we end up with a value of 5.09 times 10 to the power of minus 4, and that's going to be in, of course, moles itself. That's the first bit of our calculation done. Now we need to find the number of moles of iron 2 plus, but it's going to be in, again, 25 centimeters cubed. Just be aware that this volume can always change, but yeah, you're going to do that by, of course, timesing by 5 again, because we've got a 5:1 ratio. So I've got 5.09 times 10 to the power of minus 4, and that's going to be times by a value of 5, and what we end up with is 2.545 times 10 to the power of minus 3. Now just be aware, when you do these calculations, you need to give each line to at least three numbers here, and then if there is anything left over, you can give it to ... So yeah, we've worked out the moles of iron 2 plus in 25 centimeters cubed. We're about in 250 then. That's our third step. So iron 2 plus, and that's going to be in 250 centimeters cubed this time. That's going to be equal to, of course, 2.545 times 10 to the power of minus 3. That's our moles in 25 centimeters cubed. Divide by 25 to get the moles in 1 centimeters cubed, times by 250 to get the moles in 250 centimeters cubed. Now you do that and you end up with 2.545, and that's going to be times 10 to the power of minus 2 in this case, and that's how many moles we've got itself. So there's, of course, our third step done. Now the next thing that we need to do is to find the mass of iron, which of course we're going to use to find the percentage by mass of iron in the final step. So yeah, the mass of iron is just going to be equal to the moles times by the MR. So in that case, I've got 2.545, and that's going to be times 10 to the power of minus 2. That's how many moles I've got. And then, of course, I'm going to times by the MR of iron, which is going to be 55.8. I do that and I end up with the value of 1.42, and then we're going to go with ... and that's going to be grams itself. Yeah, there's our next mark over there to find the actual mass of iron itself. But if we've got 1.51 grams, as we planned out before, to find the percentage by mass of iron, what we're going to do is take the mass that we've got, which is 1.42 ... grams, divide that by, of course, the actual mass of the entire steel substance itself. So it's going to be divided by 1.51, and then, of course, times it by 100, express it as a percentage. We end up with 94.0%, the three significant figures itself. So here we've got a nice easy 5-mark question to find the percentage by mass of iron within a species like steel. So yeah, moving on then, let's try another question, a bit more difficult this one. We're looking at industry and we're looking at burgers. Burger. Feel free to pause the video and have a go at the following question. So yeah, we're told here sodium sulfite, Na2SO3, it's used as a preservative in some foods. Food safety legislation allows a maximum of 850 milligrams of sodium sulfite per kilogram, so that just means in 1 kilogram of burger meat. Now, a chemist determines the amount of sodium sulfite in a sample of burger meat using a manganate 7 titration itself. So reading on then, right, we're told that the sodium sulfite, so we're not actually dealing with iron 2+ in this case, it's sodium sulfite from 525 grams of burger meat. It's extracted to form a solution containing SO3 2- ions. The solution in step 1 is going to be made to 250 centimeters cubed in a volumetric flask with water. I take out 25 centimeters cubed of this, put it into a conical flask, and then the pipetted solution is acidified with sulfuric acid again, and then they titrate it with 0.01 mole per decimeter cubed of potassium manganate with a volume of 12.60 for the actual endpoint itself. Now, if you look at this, our ratio here is going to be 2 to 5 itself. That's what we've got to be aware of. In terms of our plan, we know we've got 525 grams of burger meat. We also know that, of course, our volumetric flask, it's got a volume of 250 centimeters cubed, which most of the time it is, but just be aware you can get 100 or even a decimeter cubed as well. We take out, of course, our SO3 minus 25 centimeters cubed. So SO3 2- it's 25 centimeters cubed, and of course we're going to react that 25 centimeters cubed with manganate MnO4- with a volume of 12.60 centimeters cubed and a concentration that is going to be 0.01, and then it's going to be mole per dm cubed itself, right? Now, of course, in terms of this, we've got step 1, work out the moles of manganate, work out the moles of SO3 2- using ratios in 25 centimeters cubed, in 250 centimeters cubed, and then we need to be able to find the actual mass itself of our sulfite, our sodium sulfite, not just sulfite on its own, in 525 grams itself. And then, of course, we need to find out if it actually meets our threshold of 850 milligrams of sodium sulfite per kilogram of burger meat. So yeah, we need to analyze the results and determine whether the burger meat complies with food safety legislation. So we look at it, the first thing that we do is work out the number of moles of manganate, MnO4-, and that's going to be, of course, 0.01 times by 12.6 divided by 1,000. We put that on our calculator and we end up with 1.26 times 10 to the power of -4, and that's going to be moles itself. Now, of course, we need to find the number of moles of SO3 2-. Our ratio is going to be 5 to 2. So in that case, I've got 1.26 times 10 to the power of -4, and I'm going to be dividing that by, of course, 2, because I've got the moles of manganate, trying to find the moles of SO3 2-. Then I'm going to times it by 5 itself. So in that case, I end up with 3.15 times by 10 to the power of -4 moles. So yeah, there's my first 2 steps done there so far. The next thing is of course, that's going to be in 25 centimeters cubed, but I need to find the number of moles of SO3, and then it's going to be 2- in 250 centimeters cubed. And to do that, of course, just as before, we're going to do 3.15 times 10 to the power of -4, divide it by 25 to find the moles in 1 centimeter cubed, times by 250 to find the moles in 250 centimeters cubed, and I end up with 3.15 times 10 to the power of -3 moles itself. Now, of course, I've worked out moles. Now to find the actual mass. So I've got mass of my actual SO3 2-, which isn't going to be that on its own. It's going to be in the form of sodium sulfate, so we've got to include a spectator ion in there as well. So the mass of Na2SO3 is going to be equal to, of course, the moles, which is going to be 3.15 times 10 to the power of -3, and then, of course, we're going to times that by the MR, which is going to be 126.1 itself, and of course we end up with 0.397 grams. Now that's how many grams we've got, but of course I'm going to convert it, to make life easier, into milligrams. So So I'm going to times it by 1,000. I end up with 397 milligrams. Yeah, so there's our next step done. So yeah, we've worked out our number of moles of our, of course, manganate ions, of our sulfite ions, in 250 centimeters cubed, and then of course our mass of sodium sulfite within the 525 grams itself as well. Now the next part is going to be a bit more trickier, so what I'm going to do is I'm going to make this a bit more smaller just so I have a bit more space, because we've got to think, does this actually match? Does this actually fall under the actual threshold of 850 milligrams per kilogram of bergamot? Now we've got to think about that, because that's 850 milligrams, not in a kilogram, but it's going to be in 1,000 grams itself. Now if we were to look at it right, if we've got 397 milligrams, but that's going to be in, of course, 525 grams of bergamot, we've got to scale this up, right? So what we've got to do is, of course, take the mass value of 397 milligrams, divide by 525 grams to get the milligrams in 1 gram of bergamot, and then we need to times by 1,000 to get the milligrams in, of course, a kilogram of bergamot itself. Now, of course, if I were to find the actual mass value of sodium sulfite in this case, but we're going to go in 1 kg or 1,000 grams of bergamot. What I need to do is as I mentioned, you've got 397 milligrams in 525 grams, so I'm going to divide that by 525, and that's going to give me the milligrams of sodium sulfite in 1 gram of bergamot, and then I'm going to times it by 1,000 to actually get the milligrams in 1,000 grams or 1 kilogram of bergamot itself. And so that gives me a total of 756 milligrams, right? So yeah, there's our next mark over there. You can see I've got 756 milligrams. Does that fall below the maximum? Yes, it does, and that's what we need to tell the examiner. So it's going to be, of course, less than maximum permitted level. And there's that question done there. Right, quite a challenging question, burgers. So moving on then, last question. This one's not as tricky as the last one that you've just done, but feel free to pause the video and have a go at the following question then. So yeah, we've got 2.950 grams of hydrated iron 2 sulfate, which is going to have this formula over here, and this dissolves in 50 centimeters cubed of sulfuric acid, and then we actually make the volume up to 250 centimeters cubed itself. Now just ignore this value over here, because of course that's an intermediate step. The end volume is 250 centimeters cubed, and you take 25 centimeters cubed this out, and it's going to require this volume of 21.20 centimeters cubed, and this concentration of potassium manganate itself. And then of course you need to find the value of X in the formula of the salt, so basically the number of water of crystallizations. So of course we've got our iron sulfate that's hydrated with water salt. That's going to have a mass value of 2.950 grams. That's a hydrated mass, but we want to find the anhydrous mass of just iron sulfate on its own itself, because this one over here is just going to be iron sulfate and then .XH2O itself. Yeah, so what we need to be able to find is the mass of iron sulfate, so we can actually do this calculation, because the remainder would actually be water of crystallization. So yeah, starting off then, we've got a volume of 250 centimeters cubed, so that's going to be of course our standard solution, and that's going to contain iron 2+. They take out 25 centimeters of this cubed of iron 2+ itself, and they react that with, of course, our manganate ions. Now, manganate, we've got volume of 21.20 centimeters cubed, and then, of course, a concentration of 0.01, and then it's going to be moles per decimeter cubed itself. So, yeah, the first thing to do is to find the moles of manganate in 21.20 centimeters cubed, then find the moles of iron 2+ in 25 centimeters cubed, then find the moles of iron 2+ in 250 centimeters centimeters cubed, and then we're going to find the mass of iron sulfate itself, which is step 4. Work out the difference between the mass that we've calculated versus the hydrated mass over here. That's going to be step 5. And then of course, right, we're going to work out the moles of water, divide by the smallest moles, just do a normal water crystallization calculation for step 6 itself. So yeah, the number of moles of my manganate ions to begin with is going to be equal to, of course, it's going to be 0.01, the concentration times by the volume. And what we end up with is 2.12 times 10 to the power of minus 4, and that's going to be moles itself. Now the next thing is to find the moles of iron 2 plus, and that's going to be in 25 centimeters cubed. So yeah, I've got a 1:5 ratio again, just like how we had in the original questions. And of course, I'm going to take a value of 2.12 times 10 to the power of minus 4, and I'm going to times that by 5 itself. That leaves me with 1.06 times 10 to the power of minus 3, and it's going to be, of course, moles. So we've worked out the moles of iron 2 plus in 25 centimeters cubed. The next thing that we need to be able to do is, of course, work out the moles in 250 centimeters cubed. So the number of moles of iron 2 plus in 250 centimeters cubed is going to be equal to, and then it's going to be 1.06 times 10 to the power of minus 3, divide by 25 to find the moles in 1 centimeter cubed, and then we're going to times by 250 to find the moles in 250 centimeters cubed. So we do that, and what we end up with is 1.06 times 10 to the power of minus 2, and that's how many moles we've got itself. So there's going to be, of course, our third mark. Now the next thing that we need to do is, of course, find the mass of iron sulfate itself, and to do that, what we're going to do is take the moles, which is going to be, of course, 1.06 times 10 to the actual power of minus 2, and then we're going to times that by the MR of iron sulfate, and that's going to be 151.9 itself. Of course, there's my MR. I'm going to times them together, and in my calculator I end up with 1.61, and then it's going to be ... I'm going to leave it like that for now. Now the next thing to do is, of course, because we've got the mass of iron sulfate and the moles of iron sulfate, technically we need to find the difference between, of course, this mass over here and the mass of our iron sulfate that's hydrated itself. So to find the mass of water, what I'm going to do is, of course, take the hydrated mass, which is 2.950, subtract the actual anhydrous mass, which is 1.61 ... and what I end up with is a value of 1.33, and then we're going to go with 9 there just in case as well, ... itself. Yeah, remember, you're given at least 3 numbers, and then you can leave it as ... That's fine. So yeah, I've got the mass of that now. Now I need to find the moles of water. So of course, I'm just going to do 1.339 ... divided by 18, which is the MR of water, and then I end up with 0.0744, and then of course it's going to be ... itself. That's how many moles we've got of water. Now, of course, one thing to bear in mind before we move on is that the number of moles of iron 2 plus in 250 centimeters cubed is the same as the moles of iron sulfate itself. So of course, if we look at this in terms of a water of crystallization calculation, iron sulfate, the number of moles we've got is 1.06 times 10 to the power of minus 2, and then water, the number of moles we've got is going to be 0.0744. Pardon my actual switch between standard form. I just use whatever comes out in the calculator because it's easy. I don't make any silly mistakes. So yeah, I'm going to look at which one's smaller, and of course it's going to be this number over here, 1.06 times 10 to the power of minus 2, and then I'm going to divide both of them by 1.06 times 10 to the power of minus 2, and what I actually end up with is a ratio of 1 to 7 itself. Now, of course, I've rounded that number, so we know, of course, our formula of our species, we get another mark over here, is going to be, right, I'm going to write it at the top over here because I've just run out of space. I've got iron sulfate, and then it's going to be big fat dot, and then we've got 7 lots of water of crystallization attached to it. And there's the final bit there, done, right? So we followed through all the steps, and we've got all of the marks possible in this question.